write some stuff. So, what is a reciprocal function? The reciprocal of any function is just if you put that function on the bottom. So what we're going to figure out how to do is how to graph and look at the characteristics of 1 over, and in this first lesson, we're always going to put a line on the bottom. So what does 1 over any line look like? And the idea is a simple idea. The original y values on the line become 1 over y. Because if, right, there's your original, f of x is your original y value. Now you have 1 over f of x, you have 1 over your original y value. And it's going to look like this. We're going to start by graphing the line that's on the bottom. This is done in green right here. Y equals x minus 1. You know how to graph that because it has a y-intercept of minus 1, a slope of 1. So go up 1, over 1, up 1, over 1, up 1, over 1, up 1, over 1. And we could label a lot of these points if we wanted to. Like, for example, here I have the point 4, comma 3, right? When we go to graph the reciprocal graph, that point 4, comma 3 is on the new graph as 4, comma 1 over 3. That's the only thing that changes, is that your y values become 1 over. Now, a couple of interesting things happen. What do we do right here on the green graph? I have 1, comma 0. But if I do 1 over 0, that's not allowed mathematically. We're not allowed to divide by 0. So, anytime the original graph has an x-intercept, where the y value is 0, that's going to be a non-permissible value. And we will have a vertical asymptote at every single non-permissible value. So there's a new word, asymptote. In mathematics, on a graph, an asymptote is drawn as a dotted line. I would recommend having a red pen, doing it in a different color. It needs to be dotted. It's actually not part of the graph. It's just there to help you with the graph. And it represents here at x equals, right? And we write the equation of our asymptote as whatever the non-permissible value is. The equation of vertical lines are always x equals. So equations of vertical asymptotes are x equals, and then you just write down the non-permissible value there. The x equals 1 is your vertical asymptote. Next, we can do a whole bunch of points. Like, for example, here I have 3, comma 2. Does it make sense that this, in red, this would be 3, comma 1 over 2. And here I have negative 2, negative 3, then I would have negative 2, comma 1 over 3. But there are 2 places on this graph, which I'm going to show in purple, which are the same on the red graph and the green graph. What y value could you put in so when it changes to 1 over y, it actually does not change? Does that make sense? There's a y value you can plug in. 1. If you plug in 1.
Interruption. This is just for any students that are golfing. The golf has been postponed, and it will not happen today, as well as any other outdoor sporting events after school. So, as well as any drills that will put students outside. So, anything that is outside at this time will be postponed, but golfers do not leave to go as the event has been canceled. Thank you.
They should have alarms outside. We should practice outside fire drills where you have to go inside.
Right? But then we'd be outside at the start.
They have to plan it so that it's like right before school, have a new kind of alarm system. Oh, we have to get inside outside fire drills.
Isn't that just a lockdown drill?
No. The lockdown, if you're outside, you're supposed to just run away.
So I'd rather
They should have speakers outside for lockdowns. Just like, run away. Run away.
That was intimidating, but when we looked down.
The other y value that doesn't change, you're right, here. This purple point is 2, 1, and it's on the red graph and the green graph. And there's another y value that doesn't change. Any guesses what the second y value would be?
-1.
-1. So at this point, in this case, is at 0, -1. It doesn't change, because if you did 1 over -1, you still have -1. So the big idea is that we can graph a reciprocal graph if we just draw our original one and do 1 over. But then some weird things happen, like the non-permissible value asymptote. And there's another asymptote, the horizontal asymptote, that happens because our y values on our green graph, there's arrowheads on the end, keep getting bigger and bigger positive numbers and bigger negative numbers. And if you picked a really big y value, like 1,000, the reciprocal would be 1 over 1,000. And 1 over 1,000 is close to what number? It's close to 0. If I did a bigger number, I'd have 1 over 1,000,000, I'd be even closer to 0. But will I ever equal, is there a really big number you could plug in that would, if you did 1 divided by that, you get 0? Well, infinity is not a number, it's a concept, but not a number. But we get closer and closer to 0. So there is a horizontal asymptote at y equals 0. And what's going to happen is once you've got both of your asymptotes and a few points, you then just draw your graph towards your asymptotes. Now this is really busy, all on one graph, so what I like to do is I like to draw the original on one graph and draw the reciprocal separate just to keep things cleaner. And we're going to look at that with example 1. And in fact, in example 1, we're going to add to the instructions and graph. Because it just asks for the vertical asymptote. But we can really see the vertical asymptote by looking at our graphs. So first, in green, I'm going to graph the bottom, y equals 4, x minus 3. This is a line, you know how to graph lines. We could start with our y-intercept at minus 3. I'll label that point 0, minus 3. I would go up 1, 2, 3, 4 over 1, so I would get the point 1, 1, and then I go up 4 again and over 1, so I would get the point 2, 5. I can double check if these points are right. If I plug in 2 for x, do I get 5? 4 times 2 minus 3, yes. 4 times 2, 8 minus 3 would be 5. So I can plug in my points, sort of like a table of values, to double check them. And I have a straight line. Now, a very important point on this straight line will be this x-intercept. How do we find an x-intercept? It's not easy to see from the graph this time. We find an x-intercept algebraically by making the y value equal to 0. If I make the y value equal to 0, it is not hard to solve for x. Move the 3 over, divide by 4. So 3/4, 0 is my x-intercept. Then on my reciprocal graph, we're going to first start by drawing asymptotes. Our non-permissible value, and I might even write it up here, my non-permissible value in this case is x cannot equal 3/4. That's bad, because if I had x equal to 3/4, I would divide by 0. That's my x-intercept on my green graph. It is going to be a vertical asymptote. X equals 3/4 is the equation of that asymptote because it's a non-permissible value. And almost every single line either goes up or down forever. So we will have a horizontal asymptote at y equals 0. The only time you wouldn't have that horizontal asymptote is if your original line was flat. Like if you had an original line y equals 7, you do the reciprocal of that, you would just get always 1 over 7. And it will be a flat line. And there would be no asymptotes whatsoever in that graph. But almost all the ones we get will be y equals mx plus b. So they'll have an x-intercept and they'll have an asymptote at y equals 0. So I'm going to graph y equals 1 over 4x minus 3 in blue. Do I have some points? Yes. I have 0, negative 3. That's going to be 0, comma 1 over negative 3. I have 1, comma 1. That's going to become 1, comma 1 over 1, which is still 1, comma 1. I have 2, comma 5. That'll become 2, comma 1 over 5. And we could do more points if we wanted. But if you have a point and you have asymptotes, the asymptotes are there to help you graph because your graph gets closer to the asymptotes. So even if I just have this single point here, I know that it has to get closer to this asymptote and closer to this asymptote. Same thing here. It's going to get closer to this asymptote and closer to this asymptote. And this is our final graph. So what's the vertical asymptote? It's right here. X equals 3/4. But now we've done the entire graph. It looks a lot different than the original graph. The asymptotes are a new thing. And with the asymptotes, the graphing gets really particular. Math is particular all the way through. They want you to be careful. There are 3 ways you can lose marks with asymptotes. Each time you lose a half a mark. Okay? I'll do it in bright yellow. Method 1 for losing a mark in an asymptote is to be careless and go through it, and then oh, if you go through that asymptote, you just went through a non-permissible value. That's not allowed. Lose a half a mark. So do not go through vertical asymptotes. Next year in grade 12, there are some situations you're allowed to go through horizontal ones. We're not going to worry about that now. But never can you go through a non-permissible value. Method 2, you just get closer and closer and closer, and the last minute you're like, oh yeah, I'm doing well. And you don't pay attention at the very end, and it goes away from the asymptote at the end. That's going to lose a half a mark as well. Because the asymptote is there so that you get closer and closer and closer to it. So that's mistake number 2. Then there are those people that are afraid that they'll go through it and just stay away, right? This is like as a former soccer coach of 5- and 6-year-olds, it's the super frustrating thing where every kid seems like they have to stay 3 feet away from the ball, and all these kids like, someone just go and kick it. Or if another person has it, everybody just comes close and then stops 1 foot away. No, you have to get closer and closer and closer to that asymptote. So that would be another place where you could lose. Okay, so I'd like you to try 4 and 5, and if they just ask you for vertical asymptotes, take the time and graph them as well.